Hello ladies and gentlemen, it's again Alexis from Tailored Motor TV. And this time I want to talk to you about gears, because we want to offer gearboxes in combination with the motor to have the perfect solution. So I spent some of my time in the past thinking about gears, and I tried to recap that for you. And inspired by other YouTubers, I started preparing myself through videos and drawing you stuff on a whiteboard, so it's maybe easier for you to understand. Let's start with the three basic types of gearboxes we want to use, and also the, I think, most common used in the industry, where we have the worm gear, where we have a screw turning in this direction and moving a big wheel like this. It's the only one that has 90-degree angle in it. Usually you see that on wiper motors and many mechanisms where you need a slow output. The worm gear is a good solution. A planetary gearbox, excuse my drawing, I will edit in a better picture of a planetary gearbox, is widespread in robotics, has the advantage that you come in exactly aligned to the output, so it's just another cylindrical gearbox you add to your cylindrical motor. Everything aligns nicely, so that's the advantage of the planetary gearbox. And we have the simple Spur gearbox, probably one of the easiest one. When we come in on, now if you want to reduce the speed, which is usually what you want to do with an electric motor, because the electric motors can always spin faster if you adapt the rotor design to bear that forces, but slow turning, high torque electric motors are usually way more difficult to build. So usually you reduce by using your gearbox. So you come to a small pinion, to a large one, again to a small and to a large one. So we have two stages here of gears aligned behind each other. And so that's the classic Spur gear. And usually you come out at another place where you come in. From a user's point of view, the worm gear has the big advantage of really making a big reduction, especially if you have a one-pass worm. You can make a really big reduction step in just one stage of gearbox, with the backdrop that you usually lose some efficiency. I mean, if you make a one-pass worm gear, you are at 70% or even below 70% efficiency. So you produce a lot of heat just in the gearbox. Planetary gear has the advantage, if you look at this maybe a little bit better image, the planetary gearbox has the advantage that you have three gears transmitting the power from one side to the other, or the central gear also is in interaction with the other gears at 3 points, so you can transmit more torque if your gear is close to having no backlash. I mean, if you have too much backlash, two of these wheels will be idling while the next one is doing all the work. But you can also, because you have these three in interaction, you have the statistics helping you to reduce the backlash. The inconvenience of this gear is that you need an outer hollow gear, where these three planets of the planetary gearbox are running in, and this hollow gear with the tooth inside is way more difficult to manufacture than if you have the tooth on the outside. The Spur gear, yeah, as I said, has usually a little bit more backlash than the planetary gear and is a bit larger. You don't get that torque density, but you don't have the inside teeth of a gear and the hollow the hollow gear, so it is usually more cost effective, cheaper to manufacture. From the worm gear, everything changes with the worm you have. Usually you want to go to as big as possible worm wheel, but of course you are somehow limited. And so because the larger the gears, that's a general rule about gearboxes. Make the gears, if the gears have a lot of teeth, they are easier to manufacture and they are more comfortable. The gears are more comfortable in operation than if you make them too small. And so here too, usually you will have about minimum of 20 teeth on that secondary gear, on that worm gear. That I will explain later. But suppose we have here 20. We have here 20 teeth. Oh no, let's take 30. 30 teeth, right? And so on this we have 30 teeth. We have a one pass worm, which means at every turn of the worm we make one tooth on the secondary, on the output gear, which then makes us a 1 to 30 reduction, right? Now if you have a two-pass worm, which means that we have two spirals, two screws going over the length, and if we look from the front we will see two starting points. So that's the starting point of the red screw and that's the starting point of the blue screw, and after half a circle the blue screw disappears under the start of the red screw. And so if we make one turn here, we move our secondary or output gear by 2 teeth, so we get a reduction from 2 to 30, which is 1 to 15. Of course we can do the same with 3 and with 4 passes, and so here we get 1 to 10 and here we get 1 to 7.5 reduction. You usually can't make more than 4 passes or 4 starts of your worm, because the different passes come too close to each other and you don't have enough flesh to really make a strong tooth and have the teeth in between. So even 4 passes is not too common. The efficiency becomes better the higher you go, because you have a steeper angle. So here you have very flat angle and it becomes steeper and steeper the more starts you have on your screw. It's not exactly visible on my drawing, but it's understandable, because if you have to pass by the 2 other starts with this, you have to go steeper, and that reduces your losses. So it becomes more efficient, which also has one inconvenience if you want something that automatically stops if you stop your motor. If you have a one-pass worm gear, you stop the motor, you will not be able to turn your worm wheel, your output side. It will block itself, and that can be a safety feature, can be very useful for what you are doing, but that shows you the inefficiency of the gearbox. That's the friction you generate, and that generates losses. 4-pass, you can turn it backwards, so you can turn the output side, and usually you will turn the motor in a faster way, depending on the materials you have and how much cogging you have on your motor, of course, and how big is the reduction, that the reduction factor, which means how many teeth you have on your worn wheel. For the planetary gearbox, here I have it again from the front side. I think a quite common way to use it as a reduction is that you have the inner one as an input, and you have the three outer ones that are running around, so they will move in this direction like that, running around with the teeth of the hollow gear outside. And then you have a kind of cross going over these three, concentrating that power into a shaft that comes to the outside, and that makes you one stage. Of course, you can concentrate this power onto a shaft, which again goes to a sun wheel. Usually you call this the sun, and this around you call this the planets, because they're evolving around. So you get the force out of the planets, put it into the next sun, and then you can make a multi-stage planetary gearbox, which of course will also add up your backlash, but in some cases this is totally acceptable. If you make spur gears, you have three ways of making the gears themselves, which also applies to the planetary gear. I mean, the planetary gear is just a special case of a spur gear. And so the easiest way to make teeth on gears is straight teeth, which has the advantage it's simple to make, and you have all the forces straight, perpendicular to the axis. So if that's the axis, you have the force exactly in this direction. If here we have the axis, if we go helical, the force will be always perpendicular to the tooth, right? Because the tooth only can push into the direction of his, on the normal direction to his surface. And so you get a force that pulls on your shaft or pushes on your shaft, depending, and that force, of course, you have to catch it with the housing, and that's more work and more complex, but it has a great advantage. It's way more quiet to have a helical gear than to have a straight gear. I come back to that. To avoid that problem of having one force pulling on the gears, very early the Herringbone Gear was invented, which is basically a left and a right helical gear in one gear. The first manufacturer in France building this was Citroën. So maybe you know the Citroën logo, which is like that. That's the Citroën logo you see on in front of the cars, and that came from that gear design. And Citroën, by the way, made a gearbox with this design for the Titanic. Funny historical facts around this, but this one is very difficult to manufacture. Now let's go back to why does it make noise? Why does a straight, if you have a straight gear, let me show you with these two pens, you come on, the gears touch each other over the whole line and have to go past each other. And that at every tooth touching the next one makes you a hit. And in older cars, stick shift cars, when you had the reverse gear and you drove reverse with some speed, you hear that kind of singing of the gearbox. You don't hear if you go forward. It's because the backward gear is straight and the forward gear is helical. Because if you are helical, your teeth will meet like this and will touch at one point and glide like this, which is way smoother. It's way smoother to operate, and that's why most of the gearboxes have helical gear, to avoid noise. If you build a race car, though, if you build a race car, you make straight gears, because noise, you don't care about noise. There are great videos on YouTube where you really hear that straight gear singing inside the car, besides the fact that you also have a very loud motor, so you don't care. And you can make everything lighter and easier. So on a racetrack you don't care, but in most other cases, if you have normal cars driving around, if you build robots, if you build at least a medium quality household device, you will use helical gears to avoid the noise. Now about the manufacturing and why is herringbone so difficult to make. Usually you cut your gears using this kind of cutter on a CNC mill, and if you have a large cutter you have large teeth and you make a large chip. And so if you have this disc, you can cut your gear like this, you rotate your gear one step at a time and you drive through like this and you cut your teeth. Here, even easier, you cut your teeth like this. If on the herringbone you want to cut like this, you will destroy the other half of the herringbone. So, one option is, instead of having your discs turning like this, you have a very small cutter that goes like this inside the tooth and cuts. The small cutter, of course, has smaller teeth, and the smaller teeth make smaller chips. And we have less teeth, that's the second point. I mean, on this, I just drew 4, but you can imagine you have way more teeth on this around than here. So you just get more material out. Another way to make a herringbone is to have just one tooth and go back and forth. Let me check. What was the name again? The official... Yeah, a plow, like a plow. So like a plow, a snow plow or whatever, plow on the field, you just have one tooth, move that back and forth and produce the chips. So you can move it into the middle here and then you move it out, and you move it in and you just get one chip at a time. That's very slow, it's very zen to watch. I've seen a machine on YouTube that makes that. They probably take several days to make a big gear like this. So that's the reason why herringbone is not really a good option unless you're really willing to spend a lot of money to have the best solution. Now, if we have a closer look at two teeth of a gearbox. So here we have the red gear and the green gear on the top, and we have these teeth interacting, and you see that the side of the tooth is slightly round. It's an involute gear, it's called. It's because they both roll on each other, and that makes that you have a better distribution, and it runs way more smoothly. In theory, you say they touch at exactly one point. So you have the nominal diameter of the gear, of the red gear, which goes through this point, and you have the nominal diameter of the green gear going through this point, and that's the point where these two circles meet each other. The size of the teeth is usually standardized with a module. So you say that if you have a module of 1, that's this formula, the nominal diameter is the module times the number of teeth. So if we have a 30 teeth gear with a module of 1, the nominal diameter, which is basically the diameter of this circle, not the one of this outside, the nominal diameter will be 30 millimeters. And so, I mean, you can start with module 0.01, probably if you are in the watch industry. In the field we are operating, we'll have the smallest one will be 0.5, I tend more to go into module 1 for having something between 1 and 10 Newton meters of output. It's a decent module. And if of course you go into cars, I think cars will have 2 or 3 as a module, and you can go up to way bigger if you have a steamship or whatever. Now there is also, like we have here on the worm gear, there is a limitation kind of rule for gears, is the 13 tooth rule. It's very difficult to make a gear below 13 teeth because it gets less and less linear, and you have more and more the distortion of your gears due to the diameter, to the small diameter in comparison to the size of the tooth. And so if you come close to 13, you start reducing the module and make smaller teeth, that for the same diameter you get more teeth again. But of course you can't just reduce the teeth, because the smaller your tooth becomes, the smaller becomes the section you have here, and you end up at the point where your tooth breaks off at this point. That's one of the failure modes that you usually have in gears. It's just you just completely break them out of the wheel at some point. So you want to keep that foot of your tooth, you want to keep that foot as wide as possible. And at some point you will have this tooth interacting here. Depending on how your teeth are rolling, you will risk to have an interference here with this corner here, or you get this corner here interfering here with that tooth at the moment it's rolling out of that tooth. So that's why I said the bigger the number of teeth is, the more comfortable it is, because it's very close to being linear, and you have several teeth interacting in the same time. Because now if you have really small numbers of gears and high bending of your gears, usually you have just one teeth working, or maybe 2, and if you have a large number of teeth, you have more teeth doing the work in parallel, and you don't get these problems that you have to cut out the foot of your teeth to get the room free for the tip of the corresponding tooth. And to adjust this, there's something that's called the profile shifting of the gears. That's when you start shifting, usually if you have large tooth number, usually you have a height of a teeth. The height of the tooth is 2 times the module. So if you have module 1, the height of your tooth will be 2 millimeters. And you try to have this point in the middle of the tooth, so you are at about 1 millimeter from outside with module 1, as I said. And if you start running into trouble like having to cut out the base of your tooth, then you can start shifting the profiles into one or the other direction. And then instead of having 1 and 1 here, you will maybe start moving here to have it 0, 0, 8 and 1.2 on this side. That's really the art of making gears. I'm still diving into the details. How exactly do you make that profile shift to completely optimize that you don't risk having your tooth breaking off on both sides of that pair? Because of course both sides have an influence, and you always, if you are helping one side, you're punishing the other side, and you have to find a compromise like it always is in engineering. It's always about finding compromises. The usual failure modes you have in gears, one is just having wear, so you just wear off the surface of your tooth, because there is always friction, and you just make very, very small chips, and you have a little metal powder, you generate some metal powder, and at some point you have eaten up your tooth completely. To avoid this, you start hardening your teeth. That of course only works with steel. If you have a bronze gears, or if you have plastic gears, you can't harden. But if you have steel, you can start hardening your steel. And then you run into the next problem, which is called pitting. So, you have the hard surface and you have elastic steel under the surface. Why do you want to keep the steel under the surface elastic? Because if you harden it completely through, it will break even faster. The harder your material is, I mean, drop your cup of coffee and you will see, the harder the material is, the faster your crack is growing through the whole piece and it breaks apart. And that's, if you have something that's elastic or even a little bit ductile, so it can accept plastic deformation, it can flow kind of. If it can flow, it will stop your cracks from moving through the material and make it way more durable. So you're just hardening the surface. Now what happens if you press in with some force here from the top? No, other color, let's take another one. Your force comes in from the top. You push in. The hard surface doesn't barely do anything, but underneath your elastic steel is moving. And because your surface is very hard, at some point at the both ends of your pit it will start breaking. That's the small black straights I made. So you start breaking here and here, and the more and more you press and press and press, you will over the whole surface of the pit have that hard surface and that elastic underneath moving against each other, and the cracks will form and grow, and at some point you have your hard surface falling off, and then you have the pit. Here you see a nice picture of some pitting on gears. Happens also with ball bearings and all kinds of surfaces where you have a very high surface force onto something, so it can also happen with train wheels and so on. So basically that's what I learned over gears. I hope you understand it. If I couldn't make you understand, don't hesitate to contact me in the comments or other different channels, and we'll try to understand together, because if I need to explain you, I need to understand first. That's why I explain you. Thank you very much, and see you next time.